advertisement. If you cannot find any elective, this is what you can try. So again, I'm going to put this in the video so other people know. Yeah, again, this semester, cryogenic nanoelectronics, 2 parts, device and circuits at cryogenic temperatures. So you will learn TCAD simulation and also cadence layouts and post-layout simulation. We'll talk about FinFET circuit also, not just the planar. Go through noise analysis and cryogenic measurements. Okay, so if you're interested, you can think about that. Okay, so what did we learn last time? Let's quickly recap, right? Many of them I might not test you. The point is I want you to have a sense of how come eventually we have something called spin, right? We say there's something called magnetic moment. If you have current circulating, right, over an area, you create something called magnetic moment. And why this is important? Because it's going to create some torque. There's a force. Whenever you have a force, right, you're going to create a torque in the magnetic field. And whenever you have a force and then movement, that is energy, a work done, right? So this is not that important. The point is the magnetic moment is going to interact with the external magnetic field to form a Hamiltonian, have an energy. And that will govern how your spin, govern the equation of motion. Classically, the magnetic moment is related to the angular momentum by this equation, Q over 2m, where Q is the charge, m is the mass of the particle. And we sometimes just call it gamma, which is the gyromagnetic ratio, which means they try to relate the angular momentum to the magnetic moment, a good way to memorize. For electron, turn out that this then for spin, right? Spin is something that we cannot really feel it. There's nothing called spinning for an electron, for an elementary particle, because it's just a point charge, right? It's not unlike that you have a basketball, a soccer spinning in front of you that create an angular momentum. But spin itself is just a property of a particle. You just take it for granted. It has it is given from maybe the Dirac equation. It come from the fundamental physics and math. You take it for granted. Some particle they have spin, just like some particle has positive charge, some have negative charge, some are neutral, and some has spin, some do not have spin, for example, right? So but then why the scientists call it spin? Because somehow that this particle also have their corresponding spin angular momentum, which is equals to 1/2 for in the electron case or spin half particle case is plus minus 1/2 h bar. Now, if you have the angular momentum based from what we learned from the classical electromagnetics, we know that probably it also has something called the magnetic moment, okay, spin magnetic moment. It's not really spinning, but we just accept it that it has spin angular momentum, so it also have a spin magnetic moment. And the main point is that now, if you have the spin magnetic moment, then what's the relationship between the magnetic moment and the angular momentum? Now, instead of the classical 1q divided by 2m, it turned out to be g times e divided by 2m. And g is something called the g factor. And for electron, g turns out to be, right, we have the g turns out to be about negative 0.002 and something keep going. So the scientists keep trying to find out the exact value, try to increase the precision, because this is related actually to the structure of the universe. As far as I know, they use this, maybe this is even related to how much dark matter you have in the universe, from what I learned from a seminar, which I don't understand. But this G is very important, okay, in the calculation. But anyway, this G is so close to negative 2, so we can just assume that it is equal to 2, then it got cancelled. So the gyromagnetic ratio for the electron, between the electron spin angular momentum and spin magnetic moment, is E divided by M. instead of E divided by 2m. So people sometimes would tell you that the gyromagnetic ratio for the spin is like 2 times larger than the classical one. That is what you need. Now, if you can follow this, that would be great. Yeah. Because in this class, I set E equal to negative 1.6 times 10 to the power negative 19. So it's negative. That's why I put E. Now, the gyromagnetic ratio for a negative charge need to be negative because it's negative charge. You just go through all this equation. For positive charge, they are positive. Okay, for example, for proton, I forgot it's 5 or something. I forgot the number, but it's positive. For electron, it's negative 2. Okay. Now, if you understand this, that would be great. If not, treat it as a cheat sheet. In the future, you can look back. I try to summarize it, right? Save you time from reading the Wikipedia again. But what we need to learn in quantum computing or in this class is that the interaction between the magnetic moment and the magnetic field causes some change in the energy of the system. And that energy is negative mu dot B. Is the inner product, the scalar product of the magnetic moment and the external magnetic field. And this one we kind of simplify. If we go to arbitrary direction, we might need to use operator. But here we just think about up and down. So based on this, if I don't have external magnetic field, right? For example, when people draw this type of diagram here, we're talking about, okay, there's no energy splitting, what we call energy splitting, right? Here B0 equal to 0. You don't have external magnetic field. Then whether you spin up or spin down has the same energy for the whole system. They degenerate, right? But when you apply a large external magnetic field, then you are going to have interaction. And we just say that, what is the interaction? If the this is negative mu dot B. If the mu and B are in the same direction, then the dot product is positive. Then times negative is negative, right? So if they're in the same direction, then you're going to have lower energy. And that is what I'm showing here. This is mu, this is B, they are pointing down. So they have a lower energy, right? They reduce the energy by negative mu B0. Make sense? But if they are in the opposite direction, then it will increase. That is actually easy to understand, right? If you think about, for example, a positive and negative charge has the same energy in the empty universe. But if now you bring in another charged body, then the positive charge will have a larger energy because let's say the charged body is positive because you repel the positive charge, right? Then the negative charge one might have lower energy, right? Because you attract, right? So positive charge and negative charge has the same energy. The energy degenerates in a completely empty universe. The same here. In a universe without any magnetic field, spin up and spin down should have the same energy. But once you bring in the magnetic field, then they will have different energy. That is what we call the energy splitting, right? From degenerate states to the different state. Okay, now that is the main point I want you to memorize. So remember, if the spin, we're talking about electron or negative charge, is in the opposite direction as the magnetic field, we have a lower energy. If it's in the same direction, both pointing down, we have a higher energy. Don't mess up with the magnetic moment because it depends whether you are positive or negative charge. You have different relationship. Make sense? Now, if you cannot memorize, that makes sense, but just make sure that you put in your cheat sheet or you know where to look for this information. Be very careful, okay? Any questions? Now, if no question, what we can do is we should construct the Hamiltonian now, right? So now we understand that for a spin particle in the magnetic field, you have different energy. Now, I want to know how it evolved, how the wave function evolved. Then, of course, we need the Hamiltonian because the Schrödinger equation tells us that, right? What do we say? Partial psi, partial t, I h bar equals to Hamiltonian times the state. So in order to know how the wave function evolves, I need to find the Hamiltonian. So how do I find the Hamiltonian? So let me remind you that spin up, we call it the zero state in our Bloch sphere because it has lower energy. Let's look at this. Spin up has a lower energy, right? Based on the physics we use. And spin down has a higher energy. I call it state 1. Again, we have been telling ourselves since the first class, the cat notation, bracket notation is just a name, right? So I call it spin up or zero, doesn't matter. The most important is which energy state I associate it with. Okay, so here obviously I associate with a lower energy for the spin up or the zero state. Now, if you remember what we learned earlier before, how do you construct a matrix from his eigen? Maybe I should add one more state. What is the right? If it is in the under, let's say it is under H equals to negative mu dot B. Under this Hamiltonian, what is the eigenenergy of 0? Which basically is the eigenvalue of H. Right? Which is the eigenvalue of H. What is that? So basically, I'm already saying that when I do this, in this process, we already realize that under this Hamiltonian, this system, what system? And under the system of an external magnetic field pointing down B0, right? We only have two states, either spin up or spin down. These are the eigenvector of the system, right? So I should also mention this is the eigenvector of the system, or eigenstate of H. Right? You can either be pointing up or pointing down. Okay, this is given. Okay, maybe a little bit confusing, but let's say we do a lot of experiments and I tell you that this is the eigenstate of H. When you have a magnetic field pointing down, you only going to get two states. One is spin up, one is spin down. You cannot get a state that is left or right because they are not the eigenstate of this system. Now, if that is the case, how about the eigenvalue of this H in this case? If this is the eigenstate, then of course it is what we measure from here, right? So the eigenvalue, the eigenenergy will be for 0. The eigenvalue will be negative mu B. Because this is the energy that you will get when you put in the system. It is lower. And the eigenenergy of 1, it is mu B plus mu B. This is confusing. Any questions? So remember what we said about this Hermitian matrix. We say that when we do observable, when we do measurement, the wave function will collapse to its eigenvector, eigenstate. And what you get, what you can measure is eigenvalue. So I jump a little bit. In this type of, this is a type of experiment. I apply a vertical magnetic field in the Z direction. I do some measurement, Maybe I shoot a photon and see how it is absorbed or how it is emitted. You trust that I did that? And I found out that I only have two possible states. These possible states, I call it spin up and spin down. Again, I cannot see the state. It's just that I call it. It has certain state, spin up and spin down. In one of the states, it actually absorbed my photon. Then I know that it is at a lower state. Another state emits a photon, for example. Then I know it is at a higher state. I design the experiment so that I can measure the difference between these two states before I apply the magnetic field. Right? So I realized that there are only two states. Spin up, which I call 0, or spin down, which is 1. And based on when we talk about the Hermitian matrix, observable, not Hermitian, observable, when we talk about observable, we say that wherever I can measure in experiment must be the eigenstate. So these are the eigenstates. And I just told you that, you trust me, when I do the measurement, it turned out that I get these two different energy values. Then these are the corresponding eigenenergy. Make sense? Okay. Then let's go back to how we construct the matrix. Again, we learned earlier, you construct the matrix from its eigenvector and eigenvalue by doing this. By writing its eigenvalue lambda over times all the outer product of its eigenstate. Right? So to help your study, I probably should say clearly, these are the lambda 0. This is lambda 1, right? And this, I will call it, and this is 0 and 1, very clear. 0 go with lambda 0, 1 go with lambda 1, right? So that is how you construct it, and we proved that before. You need to go back, otherwise, agree with me, trust me. This is the matrix for the Hamiltonian that we have, and we know this based on experiment. And then you construct this, you find that it is consistent, self-consistent in the whole theory. Then you trust that this is the right thing. Okay? Now, what is lambda 0 again? Very good. Very good. Yeah, very good. Negative mu B0. And then outer product of 0, right? But what is outer product of 0? Do you remember? We just do it one by one. 1, 0 times 1, 0. Correct? Bracket. Lambda 1, we know it is positive. And then this time is 1. 1 is 0, 1, 0, 1. Okay? If you do the outer product, right? But now I want to do the substitution first. What is this mu? Mu equals to, if you come to here, is approximately equals to negative the Bohr magneton. Okay? So that's why we derived that earlier. But you trust me again, h bar divided by 2m. And then B0, which is a positive number. What is the matrix when you do this outer product? 1, 0, 1, 0, and then? Actually, I did something wrong, right? This is not how we write the outer product. The first one is what? Cat. The second one is bra. So the first one should be a column, right? The second one should be row, correct? Yeah. So let me erase this. Sorry for the mistake. 0, 1, 1, 0. So this give me what? 1, 0 and row times column. 0, 0. Thank you. This one, I continue the same substitution. B0. And then what Oh, the second one I still wrote it wrong. Thank you. It should be cat times bra, right? So it should be column times row. So this gives me what? 0, 0, 0, 1. You see that? And basically, I'm going to take out this one, the whole thing. Okay, I'm going to take this out. It becomes negative E h bar divided by 2m b0. Then this whole become 1, 0. Maybe let me do one more step so that you can follow. Is this okay? Yeah, because this is positive, so I take negative out, this becomes negative, right? So if you do one more step, clearly this is equals to B0, 1, 0, 0, negative 1. What is this matrix? Sigma Z, excellent, right? So this whole thing, I can write it as HZ sigma Z with HZ equals to E h bar B0 divided by 2m. Okay? Now, why do I want to do this? Because we already derived the equation of motion last time when the Hamiltonian is in the form of negative hc sigma z. Do you remember? Yeah. If forgot, go back to see it, right? So now I derive this. Now this is a real physical system, right? It has some meaning. So let's take a look. What happened? Last time we said if you have a Hamiltonian, right? If you start with the psi equals to alpha 0 plus beta 1, and if the Hamiltonian equals to negative hc sigma z, then due to the Schrödinger equation, which is again I h bar partial psi partial t equals to h psi, right? I'm just repeating. Last time we derived that, we say that, then we have Larmor precession. About ZS's. Let me just call it ZS's. Do you remember this? When we have a Hamiltonian like this, H negative HC sigma C. Right? It doesn't matter how it comes from. It can be magnetic field or whatever, right? But last time we said if you have this, we try to solve this equation. And then we show that it's going to precess about these S's, right? Right? And that what happened? Larmor frequency, which is I'm going to put in radians, omega L equals to negative 2hz divided by h bar. This is just a reminder. That's what we did last time, right? So you trust me, right? If you don't have the note, you trust me that that is how it's going to precess. Now, but now we know that hc equals to E h bar divided by 2mb0, right? Of course, we also know sigma c is just equal to 1, 0, 0, negative 1, which is not important here. Then we know the Larmor precession frequency has to be equals to, let's look at this one, right? It needs to be positive, of course, because we're talking about frequency is precessing clockwise, equals to what? E h bar to right? Because I write 2 first. I should write 2 first. 2. And then I try to write HC, which is EH bar divided by 2M H bar. Is this okay? Do you see this? Yeah. And I also missed the B0. What do we get? What is the frequency that is precessing? Do the cancellation, right? E over M, B0. Now here we did a substitution before by assuming the G equals to -2. In reality, this is actually G. It should be G, I just put everything, E divided by 2M, B0. Okay? Or more common, even for other particle, you just put gamma B0. Gamma B0, the gyromagnetic ratio times the magnetic field, give you the precession frequency. Right? So with this derivation, even when you talk about hole or you talk about proton, you will have the same equation. Okay, and this is the Larmor frequency. Right? Now, last time we already talked about Z gate, but it is the same here. Now, if I set the frequency, I still use this one. This is the frequency. And then I multiply it by T so that it rotates by pi on the broad sphere. That means if you apply the vertical magnetic field for a time equal to pi m divided by E B0, then you get a Z gate. So we did, yeah. Not pi time, yeah, but this time, right? Oh, you're saying the pi is not precise anyway. Oh, you're saying that, yeah. Of course, there will be error, and that's why you need error correction. That's why some people claim that this is analog computing, because all the rotation is like that. And indeed, so that's why E226 is important, because you need to have the precise microwave control. Not in this case, but in this case, we're talking about the vertical electric field. Now, I need to admit one thing. This is usually not used. Here it is just for instructional purpose. It's very difficult to turn on a large magnetic field, DC magnetic field, on and off quick enough. As far as I'm not an experimentalist. But Z-gate usually need no implementation, because you can do so-called virtual Z-gate. You just change your frame of reference in your calculation. Okay, so it just say this time I just read the signal as if I rotated about the broad sphere for a certain angle. And then in that case, and then because you also don't care about the global phase, right? This is particularly true for like the superconducting qubit. I need to check actually whether it's true for the spin qubit, but I don't think we are going, how to say? Yeah, we will just, they're still in the research topic, but it's difficult to turn on the DC magnetic field on and off fast enough. So this is a good instructional material, right? You can see the precession, okay? But we still need a constant magnetic field later to look at the rapid oscillation, spin resonance. We'll do it on Wednesday, okay? But just take it, have an appreciation on how it works. Any questions? Okay, so for rapid oscillation,